Hi, I'm starting a small series of videos about my desk setup, the equipment I use and how I organize my workspace. And the first project in this series is this one, a fully 3D printed speaker system. At some point I caught myself using this cheap little Bluetooth speaker most of the time. And honestly it felt really wrong. Using something that simple and cheap with the kind of gear I use is terrible. So I decided to fix that. I built a 3D printed 2.1 speaker system, transparent PETG enclosures, CNC cut PMMA side panels with black and silver accents. I wanted something that sounds good, but what I wanted even more to make it by myself and make it unique. When I started looking online for inspiration, I went down a rabbit hole of DIY speaker projects, horns, boxes, and then May-style speakers. That's when I found Hexibase, his YouTube channel and his projects on printables. His work immediately clicked with me. Clean design, clever engineering, and that beautiful folded labyrinth pattern inside the subwoofer. Two halves glued together to make the casing with a folded maze guiding the sound through the entire box. And for some reason, that maze pattern instantly became something I just had to include in my design. I'm not even sure why, maybe because it looks so engineered and purposeful. And once I had that concept in, I started sketching. But I quickly realized that I don't want two halves to be glued together. So I played around with different configurations and came up with something cleaner. A single 3D printed centerpiece made from PETG with two side walls to close it up. Then I had an even better idea. What if those side walls were transparent? That way you could actually see internal structure, the empty chamber volume, the driver mount, the labyrinth paths, and how everything fits together, even if the airflow itself isn't visible. And that's when everything finally clicked. I could start designing it for real. Now, I'm not a sound designer or an audio engineer. I don't have professional measuring gear or the experience to design speakers completely from scratch. So I decided to start from Hexibase bookshelf speaker model. I measured the internal chamber volume, the maze length, and the cross-section area, and then adapted all of that for a different driver. It is a more powerful unit, so to make it work properly, I had to increase the chamber volume, widen the cross-section, and extend the maze path. Direct scaling doesn't work for engineering projects. If you double all dimensions or something, the volume doesn't just double, it increases eightfold. So proportions go out of balance very quickly. You can't just grab any 3D model of a speaker online, scale it up or down, and expect it to sound good. You have to actually adjust the geometry for volume, resonance, and tuning. And I won't pretend that I suddenly learned acoustics from a single project. I just threw a bunch of data into AI and started talking to it, figuring out different aspects of the design as I went through that. Combining that with a few articles and calculators I found many online, I was able to get the values I needed to create proper 3D models for my drivers. I beefed up the wall thickness for two reasons. First, I needed more material to hold thread-forming screws in plastic. And the second, I know that heavier speakers perform better than lighter ones. It's much harder to make a heavy object vibrate, which is why people often use dense materials like concrete or MDF for their speakers. Initially, I even thought about pouring concrete into 3D printed cavities, but after calculating how much MDF would weigh, I realized PETG could reach a similar mass. I used gyroid and fill. I like this pattern because it looks cool and provides multi-directional strength. When the first print was ready, I started to measure everything. Tolerances, fitment, and to my surprise, it just worked. But I didn't start assembling right away. I still needed to figure out how to seal the internal volume of these speakers. I designed a 3D printed mold to pour two-part silicone into, to create gaskets. I purchased black dye to make regular transparent silicone black and starting pouring. Well, it didn't go very well. The silicone tried to escape, the mold was too tight, and I saw a lot of bubbles. Even in a vacuum chamber, it would have been hard to get rid of them, and I needed 6 gaskets total. I didn't want to spend that much time playing with silicone molds, so I decided to try TPU instead. I'd printed TPU85A and TPU95A before, but never something softer, and I knew it would be tricky. Still decided to give it a shot. I bought a spool, 3D printed a holder for it, and started printing. It was stringing like crazy, but it worked. The fit was great, and in this particular use case, TPU and PETG shrinkage turned out to be almost identical, which was a lucky coincidence. At this point, satellites were mostly complete, and I switched to subwoofer enclosure. There are plenty of 10, 12 or 14-inch subwoofers on the market that can go down to 30 or even 20 Hz. But I didn't want to make anything that big. Ideally, I wanted subwoofer and satellites to be roughly the same size. Luckily, Hexibase had his design for the subwoofer as well. If I used his design for the satellites, why not to use it for the subwoofer? Again, kudos to him, the design is just awesome. I didn't need to completely redesign it since I found the same driver, but I still wanted to adapt it for my particular setup. I added a little more material on the side so the speaker wouldn't stick out, and it increased the channel's cross-section. To keep the tuning the same, I reduced the height of the channel, but that also changed its length, so I had to tweak the entire labyrinth to make it work the way I wanted. Then it was pretty similar to the satellites. I printed the enclosure, made the gaskets, all went smoothly, and moved on to the side panels for everything. I decided to use PMMA, plastic also known as acrylic. It is stiff enough when thick enough, but it scratches very easily, so I'll try to touch it less as possible. I found 6mm sheets on Taobao and cut them on my CNC machine. Then I bought some plastic thread forming screws and tried attaching a side panel. Working with TPU75A gaskets was like a spaghetti monster. It kept escaping every time. So I used a few drops of CA glue to hold it in place and finally managed to screw everything together. At this point, they looked great and were ready for final assembly. I 3D printed driver gaskets, installed a few more screws and heat inserts, ran the cable and soldered them to drivers. Now that the speakers were complete, it was time to work on the amplifier and power supply. My friend John soldered a few things together. It was actually his idea to use transformer as the power source. And I didn't want to just leave an open board with a transformer sitting on the desk. I designed a matching 3D printed case for it. It holds 200 watt toroidal transformer, 2 big capacitors, and the TB21 Pro 2.1 amplifier board. All in one compact unit, same design language, transparent PETG, black inserts, silver screws, everything fits tight. The wiring is clean and the whole assembly looks like it belongs with the speakers. So the 2.1 system was finally complete. Time to test it. I placed the speakers on cushions to prevent them from vibrating against solid surfaces. Then I positioned a microphone where my head would normally be and disabled all filters on the microphone itself. Keep in mind that this microphone isn't designed for such a use case, for audio testing, and YouTube compression destroys sound quality anyway, so you won't actually hear it. But I'll still play some music because without that the video wouldn't feel complete. and they sound awesome. Of course, I made them, so I'm probably biased. What would be really fair is to share the 3D models so other people can try them out themselves. That's exactly what I'm going to do, so look for the link down below, I guess. Maybe someone with proper measurement equipment can actually test and visualize how they perform. And thank you for watching all the way to the end. Hit the like and subscribe buttons if you enjoyed the video, and don't forget to leave a comment, especially if you think I did something wrong. I'm genuinely curious what real sound engineers think about this design, because sound is a real rabbit hole.